Hi everyone, and thank you for joining my talk today. I'm going to talk about oldies but goodies, or why classical machine learning still rocks. Hi, my name is Dorit Baras. I'm a senior algorithm engineer in Medtronic Yokneam. I have over 15 years of experience in machine learning, deep learning, image processing, and computer vision. I have bachelor and master's degree, both from the Department of Electrical Engineering at the Technion, and I love Hello Kitty and rock concerts when available before COVID. These are pictures from my private collection. So let me tell you how the idea for this talk started. As part of my work, I supervise industrial projects. It's a collaboration between Medtronic and the Department of Computer Science in the Technion. We offer topics for projects, and we provide the data and computational resources, and undergraduate students work on those projects. Usually the projects that I offer are deep learning projects on PILCAM data, and students are very enthusiastic about it. I usually suggest that in addition to the deep learning model, the students will also train a classical model or a hybrid model, and this is the response I get. The students tell me, seriously, do people still do that? I mean, we have deep learning today. We can do things that are so accurate and have all those amazing details. And I tell them, yes, that's right, but sometimes we want something that is quick and dirty, that it's lighter and easier, and we can understand better what it does. And the fun part is that we can combine them into a hybrid model that outperforms each one of the models separately. So today my mission is to convince you that classical machine learning is still relevant and it rocks, and I urge you to use it. The continuation of the talk is as follows. I'm going to provide a very brief history of machine learning, and I want to emphasize that I am going to concentrate on classification algorithms only. I'm going to talk about the pros and cons of each approach and the considerations for deciding what to use when. And I will show a few concrete examples. Okay, so this is a histogram count taken from the review process for NIPS at 2016. NIPS is one of the two largest machine learning conferences. And at 2016, the top 3 topics were deep learning, computer vision applications, which is another nice name for deep learning, and large-scale learning and big data, which is another fancy name for deep learning. So we know that there has been an explosion of this technology starting at 2005, mainly by Hinton, Lecun, and Bengio, who are also the winners of the award in 2018, the Turing Award, for their contribution. But it started much earlier, in the early 40s, when Hebb presented the concept of a neuron, like the brain cell. And then in the late 50s, when Rosenblatt presented the perceptron, the first linear classification algorithm based on the idea of the neuron. In the mid-80s, the backpropagation algorithm was presented, and it is used to train artificial neural networks, which are considered the ancestors of today's deep learning. In between, there were other classification algorithms, such as the support vector machines and decision trees. Okay, let's talk about the pros and cons of each approach. So data. We can start training a classical machine learning model with only a few dozens of examples, and we can also train on a few hundreds of examples. Usually when we get to the area of several thousands, we are going to have to downsample. We can start training a deep learning model with a few hundred samples, and the sky is the limit. Interpretability. So classical machine learning offers, in many algorithms, ways of interpreting the model. For example, in decision trees, the nodes correspond to specific features and the thresholds. And by looking at the structure, we can understand which features are more important than others. Another example is in linear support vector machines, where we can analyze the values of the weights which are proportional to their importance. However, in deep learning, the interpretability is limited. We have millions of parameters, and understanding the exact values of a certain convolution layer will not help us understand why the output of the network was a cat and not the dog. Computational resources. So classical machine learning requires a strong GPU, while deep learning requires a GPU and a lot of memory. And the performance, so in deep learning, they can even outperform human level and achieve great results. And in classical machine learning, they can be moderate. Okay, so how do we know what to choose and what to use when? So the first question we need to ask ourselves is regarding the volume of the data that we have. So as I explained earlier, when we have several dozens examples, we usually use classical machine learning. When we get to the area of hundreds, we can use classical machine learning or lots of augmentations and then deep learning. When we get to the area of thousands of samples, we can subsample and use classical machine learning, or we can use deep learning. And when we get to the area of many thousands or even more, we use deep learning. The second question relates to the type of data that we have. If we have tabular data, in tabular data, each row corresponds to a sample and each column corresponds to a feature. This is a concrete example. So this is classical for classical machine learning. This is the raw data that most classical algorithms accept. So when you have tabular data, use classical machine learning. For images, it depends on the exact task. We can either extract manual features and represent each image as a vector and feed those to classical algorithms, or we can take the image as is as an input to a convolutional neural networks. So here again, we can use both. Video streams usually have a lot of data, so deep learning is more appropriate. And in text, again, it depends on how much data we have. If we have a large corpus of many Wikipedia pages, then we're going to need deep learning. But if we have few sentences or clusters of words, then classical machine learning is enough. The same goes for time series. If we have the value and the price of a product over time, regression can be enough. But if we have months worth data of EEG, then we're probably going to need deep learning. Finally, when we have mixed models, again, depends on the task, but many times it calls for hybrid models that combine both technologies. The next question relates to the domain knowledge. Do I have enough domain knowledge to extract the features or even to label or annotate the samples? For example, if I want to train a model that will distinguish between cats and dogs, I know that I can extract features such as the shape of the ears or the length of the tail. Or if I want to distinguish between apples and bananas, I know I can look at the color or the shape. But if, for example, I get medical data like MRI data, I personally wouldn't know which features are relevant. And given an MRI image, I wouldn't know if this patient has a tumor or bleeding. The next question relates to the interpretability. As I mentioned earlier, it's almost impossible with deep learning. So here you see an example, a real example from a paper about predicting diabetes risk with a decision tree. You can see that the features are glucose and insulin and age and so on. And by looking on the tree, you can understand the risk factors and understand why a decision is made. You also see the inception network. It is well known and commonly used. But if I tell you that what are the numbers in one of the specific layers, it's not going to help me understand why the output is a cat or a dog. Next question relates to the technical constraints for training and for inference. So training a classical model can take a few seconds, a few minutes, maybe a few hours. Training deep learning model usually starts with a few hours, but it's typically days and even weeks. And where classical models require CPU, deep learning requires GPU, at least for training. I will say that there are networks that are small enough to run on mobile devices like MobileNet. And a few concrete examples. Okay, so the first example is a classical use example of EMR data. EMR stands for electronic medical records. This is for forecasting type 2 diabetes. So this is a tabular data, which we already said that is for classical algorithms. And they have a bit over 2,000 patients, and their features are demographic and clinical and lab values. Here in the table you can see examples of some of the variables. And the authors tried various algorithms like logistic regression and k-nearest neighbors and decision tree and so on. And the area under curve, which is our performance measure, varies in the range of 0.72 and 0.87, which is not amazing, but it can still provide the physicians with information. This is one of the trees that the authors present that they learned. You see that it only has two features, BMI and triglycerides. The second example is a deep learning example with retinal images of the eye, and this is also for diabetes detection, retinopathy, which is a disease that comes with diabetes. So here the data set is large. There are 35,000 samples, and the users use an ensemble model. It means that they train several deep learning models in parallel, ResNet, inception, exception, and so on, and they take their average prediction as their output. So here you can see that the area under a curve is higher than what we've seen earlier. The results are good, and also the confusion metrics. The third example is a hybrid example of mammography and EMR data combined. Here, each sample is 4 mammography images and the corresponding clinical data. There are 10,000 patients, so there are around 40,000 images. They had 2 objectives here: to classify whether or not this patient has cancer, and category of the mammogram, whether it's normal or abnormal. And I'm not going to go into all the details, but I do want to show you some parts of their system. So in the first stage, they used classical algorithm for feature selection that reduced the number of clinical features. Then they trained several deep learning models in parallel, and they used this representation and the clinical features in order to learn the model for classification of the 2 objectives. Here you can see the results. Again, the area under curves look really good. But what is nice to observe is that the blue line corresponds to results using clinical data only, and the green using images only. But the red is the combined. And this is an example where the hybrid model outperforms each model separately. Another example that is also relates to classification of diabetes retinopathy. I won't go into details. I just want to show you that here the authors used feature extraction using deep learning, and then this was fed into a classical model of support vector machines. So let's summarize. Classical machine learning is still relevant, and it has many advantages. I urge you to use it as much as possible. Deep learning is amazing. I don't think I need to add further. And you can use deep learning as part of a hybrid model. You can either use the deep learning output scores as features with additional features, or you can learn a representation using deep learning and use that as an input to your classical model. Thank you. I'm available for any questions.